On to the calculations. We really only have a couple of equations that we're going to use for almost the majority of this unit. So it's just a matter of keeping everything straight, kind of a bit of bookkeeping, keeping the sign convention straight and all of that. But our equations that we're principally going to be using are the magnification equation, negative di over do, or hi over ho, and then the one we call the mirror equation, which is 1 over do plus 1 over di equals our focal length, 1 over our focal length. And we also know that our focal length is always 1/2 of the radius of curvature. So that's basically our toolbox for quite a while. Let's look at this problem here. We've got an amusement park mirror that gives an inverted image of a person who stands 2.1 meters in front of it. If the image is 2 times the person's height, what is the radius of curvature of the mirror? So let's say we've got our concave mirror here. I'm going to draw U as a little arrow, so that's our object. And then the distance here, come on computer, the distance here is 2.1 meters from here to here. And then we've got our image. It's inverted, and if you remember from the previous video, we're always inverted when the image is on the same side of the mirror over here, and the image is 2 times the person's height. Also, the images are bigger when they're back here and smaller when they're back here. It doesn't really matter if you remember all of that. You can kind of plug things into the equations anyway, but if you get the hang of that, it's going to make life a little easier. So we know that our image is going to be back there behind the object, and we know it's going to be inverted and all of these good things. Okay, so what are we trying to find? We want to find the radius of curvature, and really this is the only equation with radius of curvature. So we're always going to find focal length first, not always but most of the time, and then just take half of it to get the radius of curvature. So we're going to be dealing with this equation to try to get our focal length. We're given do, that is the 2.1, so I've got 1 over 2.1. Now the image distance, it doesn't give that to us directly, but over here it tells us that the image is 2 times the person's height, and it's inverted, so that means that the magnification equals -2, because it's 2 times as big and it's inverted, so we've got negative, right? Now I can use that and set that equal to negative di over do. So negative di over do, negatives go away, and if I multiply that over here, I kind of ran out of room, so I'm going to jump down here. I know that di is equal to 2 times do, the negative went away. So I can plug in here for di, I can plug in 2 do, and I know do, it's 2.1, so I just need to multiply that by 2, and I get 4.2, and that whole thing is equal to 1 over the focal length. So you can just plug this into your calculator as a fraction and then take the inverse if you like. Because they're a factor of 2 of the other, I could just say, well, this is going to be 2 over 4.2 and 1 over 4.2, so that's going to give me 3 over 4.2 when I combine those is equal to 1 over focal length, and you can invert right now if you'd like, and so you're going to have 4.2 over 3, and so we find a focal length of 1.4 meters. Oh, also, we don't have to use standard units for this equation as long as our units match. So if we plug in meters, then all of our answers are going to come out in meters, but you can use centimeters as well, and then just your answers come out in centimeters. So that's kind of nice. You don't have to worry about converting things all of the time. So if we know that that is 1.4, we just have to plug that in here. The radius of curvature is going to be twice the focal length. So 2 times 1.4 gives you a radius of curvature of 2.8 meters. Okay, let's look at one more example here. where should an object be placed in front of a concave mirror so that it produces an image that is twice the distance from the mirror as the object, but on the other side of the mirror? So let's do a little sketch to get an idea of what's going on here. We don't know its location, we just know that it is on in front of a concave mirror. So the image is going to be twice the distance. So if we say this is some distance here, this technically it should go to the middle of the mirror there. That's our object distance. Our image distance is going to be twice that, drawn approximately to scale. And if we remember, we're always upright when we're over here. And I know it's going to be bigger because I just kind of know how these things work. And so that's kind of what's going on here. And we want to know, where do we place this? And we don't have any numbers, so we can't get a number here, but we can get this location relative to the focal length is what we're going to look for. This here is di, by the way. Okay, so I know that from the given information, I know that di is equal to twice do, and if I'm on the other side, that means I've got a negative sign too, so negative 2 do. I'm not saying do is negative, I'm saying di is going to come out negative when we plug in a value for do if we knew it. Okay, so there's one of our equations. If we plug that into the mirror equation, we're going to have 1 over do plus 1 over di, which is our negative 2 do, equals 1 over the focal length. So we can combine these. This is going to be, if we multiply top and bottom by 2, not 21, we just got 2. So we're going to have 2 over 2 minus 1 over 2, so that's going to leave us with 1 over 2 do equals 1 over the focal length. We invert both of those and we get focal length is 2 do, but really we want to know where to place the object. That's what it was asked, where should an object be placed. So we're trying to find the object location or the object distance. So if we place that at half the focal length, then we will have an image that is twice as large and on the other side, and they're always going to be upright on the other side. So follow-up questions: is the image real or virtual? Well, if it's on the other side of the mirror, it's always got to be virtual because the rays don't pass through the mirror. They're always going to bounce off it, so there's no rays over here. Whenever you've got an image on the opposite side of a mirror, it's going to be virtual. Is the image inverted or upright? Well, I kind of told you from the start that it's going to be upright. If you remember that whenever they're on the other side, they're always upright, that works. Or you can think about your magnification equation, where you've got negative di over do. But this guy is going to bring a negative with it because it's on the other side, so you know that this is going to come out to be positive. If we're just plugging in the magnitudes of di and do, this is going to come out to be positive, which also tells you that it's upright. Now, what is the magnification? We can actually find that by using this information and plugging into this equation here. Let me erase this here for a second. Okay, so I don't know the values, but I know that di is equal to negative 2 do. So if I've got a negative 2 do over do, do's will cancel out. I've got a couple of negatives, so I get a magnification that is equal to 2. And like I said earlier, it comes out positive. That again tells us that this is upright. There's our answer, 2. And so there you have it. Quite a bit to kind of put together, but if you take it one step at a time and do a lot of them, you'll get the hang of it. Okay.